So this week we will cover content of week 5, which is differentiability and differentiation rules. This is going to be very important for us. From this point on, we are basically working with the derivatives of functions. So it's very important to get everything done, learn at this point, and then move for the other stuff. Well, the first thing that actually we did some work for, what is differentiability. Very quickly, with some assumptions, f is defined at a point and around that point, then f is called differentiable at a, is called differentiable at a if this limit exists, that f of a plus h minus f at a over h as h goes to 0, or equivalently, there is another version of this which is basically the same limit after you do some substitution. Equivalently, this other limit, which is limit of f at x minus f at a over x minus a as x goes to a. So these have kind of different, intuition. One is coming from the slope of tangent line intuition. The other one is coming from the rate of change intuition, but both of them should give you the same result. And if the limit exists, then we say that the function is differentiable, and we denote that value by f prime at a. And well, we will do another example today, but there is this hierarchy that you have to learn in this course. This is one of the core ideas. Historically, the discovery of all these things has been done the other way around, but now we are teaching it in a different way. Remember that we have studied limit, existence was the first thing that we did. Then we learned about something called continuity, yes? And we saw that continuity is stronger than limit, because continuity says that the limit exists, and then the value of limit is equal to the value of the function at that point. The differentiability, this is a mathematical fact that differentiability is stronger than continuity. It means that if a function is differentiable at a point, it will be continuous at that point. Obviously, at that point, it will have this limit. Okay, so this is a hierarchy that you have to remember, but the main part which says every differentiable function at a point is continuous at that point is a very important theorem, and you have to know it and use it. In the upcoming example, I'm going to use that, and we will see a little bit of details of how this goes on. Is there any questions, any comments before I move to the examples?
Sorry, just to verify that, I guess the chart that you or what you just wrote down, is that showing that I guess like the limit existence depends on continuity, and then continuity depends on
Not more dependence than just implication. So you see, differentiability implies continuity, while differentiable at one point implies the function is continuous at that point. And the definition of continuity at one point means that the limit exists at that point.
Okay, makes more sense.
Implies that. That's better. Yes. Okay. Let's do some examples. Yes. Okay. So we did, I believe, we did an example last time, but this is more like different different format of example. We are trying to find the derivative of this function at point -1. You should remember the form of this question. Very soon we will learn tools of how to differentiate a function. But if a question, an assignment asks for use the definition, that means that you have to go into the mod, do the work, write the limit, find the limit. Okay, what limit? So in this case, a is this guy here, -1. So we are trying to find the limit of f of a plus h minus f at a over h as h goes to 0. Yeah, but yeah, one can use the other format, which is x minus f at -1 over x minus -1 as x goes to negative. These two guys are going to be the same thing, but you will see that practically they may require different steps. And this is very interesting example in different ways. So let me just form this, both of these guys for our function. So in this case, this is the third derivative of, so input is -1 plus h. For x, I have to put -1 plus h. There is plus 1 there, minus -1 plus 1. That's it. Yeah. And then h. On the other hand, this other guy will give you this formula, x plus 1, the third root, this is the third root, minus -1 plus 1, the third root, and then divided by x plus 1 as x goes to 1. So I will stop here and ask you after this session, try to do this one. It's an interesting example, and it's going to have kind of the same calculation, but you have to go different, take different steps. Okay. How about this one? Okay, now let us just see what is happening here. -1, 1. So this is the third root of h minus 0 over h as h goes to 0. And right away you see that, oh, this is 0 over 0. When it is 0 over 0, you have to factor it, cancel it. Remember the vanishing factor is h minus 0. And well, in this case, see, I have h to the power 1/3 over h, and that gives me 1 over h to the power 2/3. So my limit here is 1 over h to the power 2/3. And while we see that, oh, this is the numerator has limit 1, the denominator has limit 0. But since this is h squared to the power 1/3, it is a positive. It's always positive. H squared is always positive. So that means that we are dealing with always in the denominator 0, positive numbers close, very close to 0, and that will give us plus infinity. Well, infinite limit, the limit does not exist. Well, that means that f is not differentiable at x equal to negative. This has this example is very nice example because it shows that, remember that if you have watched the videos or read the book, the textbook, you see that the main intuition comes from the slope of tangent line. And if you look at this function is going to have uh so, well, it should be a little bit like that, like that. This function actually has a tangent line at x equal to -1. The issue that comes up here is because of the fact that the tangent line is vertical. So the vertical tangent line exists, and it is a tangent line, x equal to -1 there, but the slope of vertical lines are not defined. That's why we're getting plus infinity here. So the tangent line exists. It is a vertical one, but the derivative, the function is not differentiable. So this is one special case of differentiability not being differentiable for the function at a point. Okay. Any questions, any comments before I move on and do another example?
What?
Yes,
Sorry.
go ahead, please. Please go ahead.
Sorry, you can go ahead.
Yeah, go ahead. You can ask. Yes.
I was just wondering why it's not differentiable at x equals 1. Like
Because
it's still.
you see that the limit that we found is infinite limit. Infinite limit is a special case of the limit does not exist.
Yeah, but in the graph, it still has a defined point, right?
It is defined, yes. It is continuous. It's a special case of not being differentiable, and that's it has vertical tangent line.
Oh, right. Okay.
Okay.
Makes sense.
I can move to the other one. Okay, so this is one of the good typical questions that we have. Okay, so here find values of a, b, c, for which the function is differentiable. Okay, everywhere this is not a good statement here. This should be on this guy, because here I have root x, and the function is not defined for negative values of x there. Okay, so we start with the definition. So with the definition, meaning what? Meaning that I want to go ahead and find h at, well, it's enough to check it for the separated point. The other guys, at other points, the function, the formulas are good. Those are differentiable formulas. And I will go just with the one. And for that, a plus, oh, I have two h's now there. Oh, I like that. Should have noticed that before. At 1 over h as h goes to 0. But here I see that, okay, I can evaluate G at 1. G at 1, no matter what is B, the value of B, whatever the value of B is, it's going to be the value of the function at 1. But for the value of G at 1 plus H, we have to be careful. If H, sorry, this is 0. If H approaches to 0 from the right-hand side, then 1 plus H is going to be bigger than 1. So in that case, the formula we have to use is sine of A 1 plus H minus 1 over 1 plus H plus 1, okay? And then minus B over H as H goes to 0 plus. If H goes to 0 from the negative side, then H plus 1 is going to be less than 1. And for that, we have the formula given by this, which is 1 plus H plus 1 minus B over H. Very nice. Okay, I have two limits as we have done most of the time. Now, the point is that you're trying to find values of B and C such that this limit is equal to each other. Yes. So you have to be careful here. There are some arguments you can definitely do some argument to find equations for A and B, and they're not difficult. You can definitely do that, but I am going to go a little bit different and a little bit strange way of showing this. I say that, okay, see, computing these limits is nice. Yes, if I can compute those limits, and then those will give me an equation, set them equal to each other, that those will give me an equation or equations for A and B and C. But I can't deal with simpler conditions since differentiability at x equal to 1 implies continuity at x equal to 1, I will go ahead and use the fact that if I'm assuming, if I'm trying to find that function is differentiable at 1, I will go and say that, okay, it's going to be differentiable at the end, but I will check the continuity because continuity is implied there automatically. So it means that limit of the function as x goes to 1 must be equal to the value of the function. Since this is piecewise defined function, I can do something with that, turn it to one-sided limits must exist, and they must be equal and equal to f at 1. Well, f at 1, I know it is b, yes? If when we go to x, when we go to 1 from the negative side, that means that x is less than 1, and I can use this formula for that. So limit of c to root x plus 1 as x goes to 1 from negative. This is what? This is just limit laws. Limit laws implies that this is going to be c root limit of x as x goes to 1 negative plus 1 and that is c root 1 plus 1. This is the left limit. This is the value of the function. Now let's see what will happen for the right limit. For the right limit, I have to use this guy. X minus 1 over x plus 1 as x goes to 1 from the right hand side. Well, again, I can use quotient law here. The denominator is limit of denominator is non-zero, so I will have 1 plus 1. So limit laws and the fact that sine is continuous. So it means that finding limit for sine is the same thing as finding evaluating function. So that will give me sine of 0 times a 0 over 2 must be equal to 0. Right limit is 0. Left limit is this value is this one. So from continuity, even stronger from differentiability, we get that c root 1, which is just 1 plus 1, must be equal to b, must be equal to 0. From that, I can conclude that b must be 0 and c must be negative. I found two values. This was an implication of function being differentiable will give us functions differentiable will imply that the function is continuous, and then we can go ahead and find that. I see a question, someone is saying, can we assume that it is b is equal to 1? As you see, if b was 1, then it couldn't be differentiable. The function, don't confuse differentiability with the derivative of the function. Here, you cannot use differentiation rules, because differentiation rules only deals with the functions which are good, like one piece. Differentiation rules works those cases, well, at least practically, the ones that you can go ahead, use the product rule, quotient rule, and so on. Here, there is no way other than using the derivative of function. Yes, Adam.
Hello, Professor. Do you mind scrolling down a bit?
Sure.
Yeah. I had a question about the c root 1 plus 1. Why does it become c plus 1 and not c plus 2?
No, this is, oh, c first multiplies to product is the first operation you have to do.
Oh, it's multiplies. Okay.
Yeah, this multiplies plus 1. Yeah.
Oh, okay. Thank you.
Okay. Yeah. So we have this thing now. This is nice.
Does that, sorry, we did find the value of a though.
We haven't. We are not done yet.
Okay, right.
Yes.
Okay.
So I just played around with one implication that differentiability have. I haven't checked differentiability yet. So it means that I'm not done yet. Well, that's why I haven't found a. So this gives us then our function can be updated as this is f. Okay, so was it gx for x is less than 1? I haven't been able to put any condition for a, so I'll just leave it like that. For x equal to 1, I know that b is equal to 0. For x is sorry, this was for x bigger than 1. This is for x is less than 1. This will c is negative 1. So root x plus 1. Yes, Vilo, do you have the question there?
Sorry, would you mind zooming out a bit and top? I thought I had a question. Oh wait, is it at the bottom? Does that say b is equal to 0 and c equals -1?
Yes.
Oh, okay. Thank you.
Yeah. Okay, nice. Now I can go ahead and then continue doing the work that we started with, yes? But this time now I have some values that I can plug it in, and then my differentiation will be much easier. So paste here. Okay, so here then I can update my values here, here, and here. This will be just 1, this will be 1, this will be negative. Very nice. So now I continue with the easy one, at least, as h goes to 0 minus. There's something here I don't like now. What is the function? This is the function, yes. Oh, b was 0. Sorry. Okay, yeah, that's good. B is 0. Okay. So I have to go ahead and try to evaluate this thing. So now you right away notice that we have 0 over 0 here. And then we have to multiply them by conjugate of that term. So this is plus root 1 plus h plus 1 plus root 1 plus h plus 1. And that will give me limit of a squared minus b squared. So b squared is this. A squared is 1 squared, which is 1 times h root 1 plus h plus 1. Okay, as h goes to 0 minus. And okay, see, in the numerator now, if you simplify, you get negative 1, sorry, negative h. And negative h, we factored basically the vanishing factor, and now we cancel it. And what we get at the end is negative 1 over root 1 plus h plus 1. As h goes to 0, limit laws say that we have negative 1 over root 1 plus 0 plus 1, which is negative 1 over root 1 plus 1, and that's negative 1 over 2. Remember that we are trying to find this limit here. So I found the left limit, it's negative half. Now it's time to do the right limit. I need to find the right limit of this function. Before I move to there, is there any questions, any comments? Okay, so I'll then continue from here. This is sine of a times h over 2 plus h. So I do multiply, and this is what we have. Well, I can use the product law here, and I can write it. This is limit of 1 over 2 plus h as h goes to 0 plus times limit of sine ah over h as h goes to 0. Well, the first part is easy. This is basically different ways you can do that. This is limit law. This is 1 over 2 plus 0. How about limit of sine a h over h as h goes to 0? Well, 0 plus. Can anyone tell me what is that value there?
Wouldn't it be an infinite limit?
Can you tell us a little bit more, Fabiha? Why do you see it as infinite limit?
Because if you have like h is approaching 0, so the denominator will be 0, and sine a numerator, could be another, you know.
You see, this is
Well,
sine of a times 0, yes?
yes,
That's sine of 0. What is sine 0?
0.
Okay, it's 0 over 0. Yeah.
Yeah.
So it's 0 over 0. So at least at the first step, I don't see how it will be infinite limit.
You can take out the h.
Okay, so that's not a right step. So we don't have the property for sine, which is sine of AB is not a sine of B. This is very wrong statement, yes? So I cannot do that operation.
Is it 1?
One is, who's this? Sorry, can I?
Adam.
Adam, can you tell us why it's 1?
I just think it's a rule that we're supposed to know. Sine x over x, I think.
Yes. Okay. So if you watch, I think it's
Oh,
it's
yeah. Okay.
one of very important theorems in this book, in this course, that sine of x over x as x goes to 0. This is when you try to find derivative of sine at 0. And it's 0 over 0. It's not a rational function, or it's not easy to factor out the h factor there. You have to bring in some tools. And if you watch a video on the derivatives of trig functions, you will see that this limit, using a squeeze theorem, it has a very nice proof. Using squeeze theorem, this is equal to 1. And in the same video, I explained that while x could be replaced by anything, so limit of box of limit of sine box over box as box goes to 0 is always equal to 1. Here I have AH inside sine. So my box is going to be A times h. In the denominator, I need to generate a times h, but I can multiply denominator by a. I have to multiply the numerator by a as well. Otherwise, I'm changing the limit. I'm finding something else. But if I do that operation, that will be box, sine of box over box. But you have to be very careful because this says that box must go 0, but we know that when h goes to 0, you multiply it by any number you like, that will go to 0. So this guy itself can be replaced by AH. As a result, we are dealing with limit of sine of box over box. Box goes to 0, well, either plus 0 or 0 minus, doesn't matter in this case because the limit exists. There is this constant multiple, I put it outside as a. And based on this fact here, this is going to be a times 1. Limit of sine x over x is 1, but limit of sine ax over x as x goes to 0 is a. So I can put this one back in here, and I see that, oh, I get a over 2. So let me clean up a little bit here. I put this one in the box, meaning that this was just a middle step. You have to know how to use this fact that I mentioned. And every derivative in the trigonometric functions comes from that fact. Everything, you can find all the derivatives of all trig functions on all at every given point just by using that. Okay, back to our question. Left limit, right limit must be equal. So a over 2 must be equal to negative over 2. That implies that a must be negative. we found three values for our three unknown constants. A must be -1, B must be 0, and C must be -1 for our function to be differentiable. Any questions, any comments here? Okay. Well, some questions like this, it's important that you understand that what happens when function is differentiable. So what does it mean in terms of graphs? In this case, you should notice that this guy and that guy, the function is not continuous. F is not continuous at x equal to -5 and x equal to 2, meaning that the function won't be differentiable at x equal to -5 and x equal to 2. Okay. But is there any other point? So here's what you should remember. You're basically looking for all the points at which the tangent line, you can draw a tangent line, which is not vertical tangent line. So for example, say, yeah, I can use my daughter's choice of colorful. Like you see, at this point, I can draw something, a tangent line, something like that there, something like that there. And this can be done for all the points, but at this point, the corners, wherever the graph has corners, or sometimes people say cusps for some other cases, that the tangent line doesn't exist. So this guy is also not differentiable corner at x equal to -7. So that means that not differentiable at x equal to -7. There is one more point. At 0, the function is not defined. You see, the function is not defined at x equal to 0. I don't see any point when I go up and down at x equal to 0. So that a function is not defined at point, it means that it's not differentiable, it's not continuous, so it's not differentiable. F is not differentiable at x equal to 0. And everything else, this function is differentiable, at least the parts that I have graphed. And as you can see, I believe, yeah, this is the answer. So you just need to know what's happening in terms of graph when we're talking about differentiability. So after the definitions and some theory about the derivatives, you notice that finding derivative using the function, it's the definition of the function, is not easy task to accomplish. It will need lots of work. Even in functions in polynomials, the simplest functions that we deal with. If you go beyond the third or degree 4, that's a big painful task to find derivative of a polynomial degree 4 for a given point using the definition of differentiability. This is when people has done enough work and they have provided us a list of rules that we can apply. It's like, this is a tool. You don't need to know what is working inside. It's just take it, learn how to use it, and use it. It's like my pen. Yes, this electronic pen. I don't know how it works, but the only thing I need to know is how I can apply it and use it. Yes, I don't need to know what is happening inside. The tools provided here are packages like that, black boxes like that. Well, proving them is not difficult. You can prove them. But when it comes to work with them, you need to know how they work. So this guy says the first thing, the derivative of constant function always zero. If you multiply a function by a constant, when you're differentiating, you just the constant multiple just goes out. That's constant multiple rule. That's sum of derivatives. Derivative of sum is sum of derivative. Difference of sum, derivative of sum, difference. You know what I mean. You should know the sum and difference rule. The product rule, the derivative, two functions are differentiable at one point, their product will be differentiable. And the derivative is derivative of first one times second plus derivative of second one times first one. The quotient, if the function, both of the functions are differentiable and the denominator is non-zero, in other words, the quotient is defined at any given point, then the derivative can be found by this quotient law or rule, sorry, which is derivative of numerator times denominator minus numerator times derivative of denominator over denominator squared. Some nice words show that the derivative of x to the power n is nx to the power n minus 1. And derivative of exponential function e to the power x is e to the power x. This list will go on. For example, derivative of sine. Now you can use that limit and show that this is cosine x. Derivative of cosine x is negative sine x. Derivative of other trigonometric function, we'll do one of them, but everything will come out at the most complicated cases from these two guys. But you have to now start using this toolbox and add more tools into that. And if someone doesn't ask you specifically to do differentiation using the definition, wherever it is allowed, you use these rules. Okay. Any questions, any comments before I move to some examples? I think we will have only some time to do a few examples of this. Yes, okay, so this is just practice for differentiation rule. The derivative of this, the sum rule says that, okay, I have to find derivative of first one minus derivative of second one. Then the product, the constant multiple, that says that this is just this minus this is the second one is product, derivative of the first one times the second one minus the first one times the derivative of second one. Oh, derivative of e to the power x is e to the power x. Derivative of cosine x is negative sine x. Did I write negative correctly there? Yeah, okay, sure. Derivative of cosine x is negative sine x times the second one minus cosine x times, oh, why do I have minus there? Ooh. Derivative of x cubed is 3x squared. Hopefully I didn't make any bad other algebraic mistakes, but that's how you go. For the second one, this is quotient. So we have to do the quotient rule, derivative of numerator times the denominator minus numerator times the derivative of the denominator over the denominator to the power 2. This guy, now you use the product, derivative, sorry, the sum rule, or difference. Derivative of e to the power x is 0. What is derivative of e? What is derivative of e? Someone tell me. You see, derivative of, what was it, Fabiha? Yes, please.
No, isn't derivative of e just a constant since it's e to the power 1?
It
So
is
shouldn't-
constant. Derivative of constant is
It's just 0.
0, yes. So you should not confuse it with the function e to the power x. E to the power x, the derivative of e to the power x is e to the power x. But derivative of e as derivative of any other number is 0. So this will be 0. Derivative of x is 1. E to the power x plus e to the power negative x minus this guy times derivative of e to the power x is e to the power x. How about derivative of e to the power negative x? So let's see, this is how we sometimes denote the derivative with. So derivative of e to the power negative x, I can see that as 1 over e to the power x. And then I can use quotient rule and write that this is derivative of numerator times denominator minus numerator itself times the derivative of the denominator, and the denominator is squared. Derivative of constant 1 is 0 times e to the power x is 0, and derivative of e to the power x is e to the power x. And we are dealing with negative e to the power x, e over e to the power x squared. This cancels with that, and with that, and then we get negative 1 over e to the power x, which is the same as negative e to the power negative x. When we study chain rule, you will see that this is just a simple rule of differentiation, and that will give me minus e to the power negative x over e to the power x plus e to the power negative x squared. Derivative of this function will be derivative of first one minus derivative of the second one. And then I have product. Derivative of first one is 1 times the second plus the first one times the derivative of tan x. I'll just write it there. Then you use the constant multiple rule. This is this guy. Now, I have been saying that if you know derivative of sine x, you can find, well, actually derivative of sine at 0, you can find derivative of everything else, every other trig function in any other given point. How about we apply this one, try to see how far I can do that. For tan x, this is derivative of sine x over cosine x. I will use the derivative of sine and cosine to find this, but derivative of cosine x, you can find it just by knowing derivative of sine. So here, then this is derivative of numerator times the denominator minus numerator times the derivative of the denominator over denominator squared. Derivative of sine is cosine. There is another cosine here, so this will be cosine squared. derivative of cosine is negative sine times sine is negative sine squared. There is a negative sign. This will be plus sine squared over cosine x squared. You can write it either there or there. So cosine squared plus sine squared is 1 over cosine squared x. And that's same as writing 1 over cosine x to the power 2, which is secant squared. So I found derivative of tan, it is secant squared. Derivative of tan inverse, the inverse function. This is not 1 over tan. You have to be very careful. It's not 1 over tan. It is tan inverse. For that, we need to know a little bit more, but I will write it here as the derivative is part of our differentiation table, and it is 1 over 1 plus x squared. We will learn about that in the next session or maybe after that. But that's, you have to be able to differentiate all these functions and use the differentiation rules as we go on. I have gone over time a lot. Okay, let me pause the video.